Welcome everyone to our week 9 of graduate statistics course at the University of Cincinnati. We have covered so much ground already, and you guys are working so hard. And I know, again, I'll say it one more time, how much I appreciate all the effort that you're putting into this course. And I really, truly hope that it is helping you stretch your skills and think about data in ways that you haven't thought about before. And I hope this is preparing you for engaging with science in a more meaningful way from now on. So what have we done so far? Well, you guys have been introduced formally to an area of statistics that we call descriptive statistics, where you learned how to explore data distributions by plotting histograms and box plots to look at the shape of the distribution, the spread of the distribution, where the peak of the distribution is, the center of the distribution is, and then you learned how to get measures of these properties of the distribution: center, spread, and shape. You have learned how to create interesting graphics to display differences between means, the bar plots, and the line plots, and also to express relationships between variables in things like scatter plots. You've also learned how to use contingency tables to deal with data that is not numeric, but categorical, such as the number of promotions of males and females, right? Which requires things like contingency tables that expresses who was promoted, how many were promoted, how many were not, based on gender. And because, promotion is a categorical variable with two levels, yes or no, you can't compute means, but you do have counts that you can present in interesting ways, right? So descriptive statistics allows us to present data in ways that others can quickly grasp what the patterns are that are meaningful within the data, right? And then we need let's say that, let me track back. When you describe your data using graphs, you are revealing patterns in your data. Maybe one mean is higher than the other. Maybe the proportion of males being promoted is higher than the proportion of females being promoted. So we are sort of helping ourselves, and if we're presenting the data to others, we're helping others see what is important in the data with respect to the types of questions that we're asking. Now, this is just one step, because the particular patterns that we're seeing, which could be a difference between means, which could be a relationship between two variables, may be there just due to sampling error, right? Because we're looking at data from one sample, and we really want to make inferences and statements about the full population to which that sample is part, or of which that sample is part. So if we were to get multiple samples from the population, then it is possible that every time we'll get a slightly different sample mean, slightly different mean differences in the sample, right? If you get samples from if you sample from two different groups, maybe the means are different between these groups in terms of, performance in the GRE score, the GRE test. Maybe the means are different between groups, but that difference is not going to be always the same if you sample multiple times from the population. In fact, if there is nothing going on, if there is no difference in GRE scores, let's say between males and females in the population, and you were to sample males and females repeatedly, the differences in between the means of your samples, right, in GRE score would not be zero every time. That's sampling error. So even though when we plot our sample data, we may be seeing differences, we need inferential statistics to tell us whether those differences are expected, are likely, are typical, that those magnitudes of differences, the strength of correlations, whether those are typical and likely to be observed under the null hypothesis. I truly, truly hope that you all are very clear about what a p-value then is. It's that probability of observing our data, of observing the differences between means in our two samples, the probability of observing a particular correlation strength under the hypothesis that really nothing is going on in the population at large. There is no correlation between these two variables in the population. The value of correlation that you're observing is pretty typical. It's pretty likely under the null hypothesis. The probability of seeing that is greater than that 0.05 mark that traditionally we have used as a cutoff. Same thing for differences in mean. If you see a difference in promotion rate that is, I don't know, 30%, how likely is it for me to observe that difference of 30% under fully, completely random conditions? Then we learned how to compute this probability. And to compute this probability, I introduced you to the concept of a sampling distribution, which is a distribution of means, or a distribution actually of any statistic that would allow us to, under the assumption that nothing is going on under the null hypothesis, that would allow us to then look at the value that we observed in our sample and see how likely is it that this particular mean difference would happen by chance alone. So first we learned to create these sampling distributions using random experiments and simulations. Then we learned how to apply the central limit theorem to construct the sampling distribution. And with a sampling distribution at hand, and if we're applying the central limit theorem, then our sampling distribution has a normal shape, with the center being the mean of your sample and the spread being the standard deviation of your sample divided by square root of n, because the standard deviation of your sample is estimating the variance, the standard deviation in the population, right? So the spread of the sampling distribution can be also calculated from the values that you observe in your sample, if particular conditions are met, including having a very large sample size. But once you have a sampling distribution, you can do some cool stuff. For example, you can start trying to estimate particular expected values of a variable in the population. For instance, the IQ of mothers of gifted children. If you take a sample of mothers of gifted children from the population, you can try to compute the mean of your sample to estimate the mean IQ of your sample, to estimate the mean IQ in the population. But of course, the mean is just a point estimate, which is like fishing on murky water with a stick. We're not going to get it right most of the times. With a sampling distribution at hand, however, we can compute with our sample data an interval that would allow us to try and estimate the mean, kind of fishing with a net. The likelihood of us actually getting it right when we estimate the confidence interval around the mean is much higher. And the likelihood of us getting it right depends on our choice of the confidence level, 90%, 95%, so on and so forth. And the other thing you can do once you have the sampling distribution is to actually do hypothesis tests. For instance, if I'm asking the question, or is the IQ, instead of just asking the question, what is the average IQ of mothers of gifted children? If I'm asking a question, is the average IQ of mothers of gifted children higher than the IQ of mothers in the general population? Then if I know the IQ of mothers in the general population, I know that IQ is just 100. If the null hypothesis is then that there is nothing going on, there is no difference, our sampling distribution, we can put the 100 in the middle, and that's the distribution under the null, and we can see what's the probability of getting the particular average IQ of mothers of gifted children in our sample, right? Assuming the null hypothesis, I can go there and see, no, the probability is very, very low of me seeing the particular average that I saw in my sample if mothers of gifted children had the same IQ of mothers at the general population, right? So I can actually test hypothesis on a mean to determine whether a particular mean is different from a particular target value. That's z-test, which you learned a couple of weeks ago. Now, not always applying the central limit theorem is possible, right? For instance, when you have small sample sizes, we can't guarantee that the estimate of standard deviation we can't guarantee that our sample will provide us with a reliable estimate of the standard deviation of the population. So we can't really construct the sampling distribution applying the central limit theorem because the spread of that distribution requires that I know the standard deviation or requires that I have a good estimate of the standard deviation of the population through the standard deviation of my sample. And when the sample is small, that's kind of threatened. So what do? How do we construct the sampling distribution then? Well, the way we do this, we construct the t-distribution. The t-distribution is kind of like the z-distribution. It's symmetric, but it does have thicker tails to compensate for the uncertainty. So you would have to find more extreme values in order for that the probability of seeing that being small enough for you to reject the null hypothesis. And a question came up during the live session, which was interesting. What happens if I have a large sample size and I run a t-test? Well, you'll be fine because the t-distribution has a center, just like the distribution, just like the z-distribution, but it also has the degrees of freedom as another parameter. So depending on sample size or group size, if that's large, then the t-distribution becomes more and more like the z-distribution, right? So if you have a very small sample size, then the tails of the t-distribution will be really, really thick. But if you have larger and larger sample size, then the tails get reduced and reduced and reduced until the t-distribution is just like the z-distribution, right? So the t-distribution is the sampling distribution that we use when we want to make inferences on one mean, but we can't apply the central limit theorem with confidence, right? So when you're making inferences or testing hypotheses on one mean, is the mean IQ of mothers of gifted children different from the mean IQ of mothers at large? You're doing inference on one mean. You may use the z-test if you can apply the central limit theorem. But if you can't, if you just have a very small sample size of mothers of gifted children, less than 30, let's say, then you can apply the one sample t-test, which you learned last class. All right. Now, you also learned last class how to test or make inferences about differences between means. And in that situation, you learned two types of possible tests. One test allows you to see differences between means when means are dependent on each other, and the other allows you to test differences between means when the means are independent from each other. So again, differences between means that are independent from each other coming from two different groups. In that case, you use independent t-tests, but you also can assess differences between means coming from a single group. Remember the anorexia study where you applied girls went through family therapy and you saw the difference in weight before and after? Those means are dependent and requires a dependent t-test, a paired t-test. So you learned how to assess the likelihood of seeing a particular magnitude of mean difference under the null hypothesis if the means are dependent. We also learned how to do that when there are two different groups. Imagine you had a control group that didn't undergo any therapy and a treatment group that underwent therapy. Then it's independent means, and you're going to compare the weight between these two groups after treatment. Then you would run an independent t-test to assess the probability of observing that particular difference that you observed. Now today we're going to move on to learn a test to compare more than two means, which is the ANOVA. In the next video, we'll get started on that. See you soon. Bye.